Yeah.
Our next speaker is Mareike Fischer from the University of Canterbury, and she will be talking about how many characters are needed to reconstruct the true tree.
Yeah, thank you. Yes, I am a PhD student with Professor Mike Steele in Christchurch, New Zealand, but don't wonder about my German accent, I'm actually German, so. Okay, so today I'm going to talk about how many characters I needed to reconstruct the true tree. And this is a problem that occurs when you are given a sequence of characters, for instance, a DNA alignment, and what you're really interested in is reconstructing the true tree. And there are various methods, we've heard of them this morning, to do that, for instance, maximum parsimony, maximum likelihood, neighbor joining, and so on. But there's one question remaining, namely, how good or how reliable is your result? Is your sequence actually long enough to give you a reliable result? So this morning I've heard various speakers mentioning things like, oh, we take a long enough sequence or stuff like that, but how long is long enough? So this is an interesting question, and that's why it was investigated before. For instance, in 1992, Churchill, von Heseler, and Navidi looked at it, and they investigated various scenarios. One of them, the 4-taxon case, and they observed that, first of all, the probability of reconstructing the true tree correctly increases as the interior edge gets longer. And also it increases as the pending edges get shorter. So, well, they illustrated this with a graphic. So as you can see here, as the interior edge increases, your reconstruction probability increases. And also they ran these simulations for various numbers of characters. And the more characters you had, the better and the more reliable were your results. Okay, another approach in 1998 was taken by Yang. He actually fixed the interior edge at a length of 5% of the total tree length. And he investigated the 4-taxon case looking at 5 different tree shapes. For instance, he had this scenario of 4 pending edges of the same length, and here we have 1 pending edge being extremely long. And and he investigated 3 methods. So we got the squares being the maximum parsimony method, and the other 2 being maximum likelihood under different model assumptions. I think it was Jukes-Cantor and the Kimura plus Gamma model. Anyways, what he found was that, for instance, for most trees, the differences between the models were not so, or between the methods were not so big. But as you would expect in the so-called Ferris zone, where you have 2 short pending branches on one side of the tree and 2 long pending branches on the other side, maximum parsimony outperforms maximum likelihood. And the opposite happens in the so-called Felsenstein zone, where you have a short and a long pending edge on either side of the tree. Here, maximum likelihood does better. And anyways, but the scenario we are interested in today is the scenario of having 4 pending edges of the same length. And what Yang found in his simulations was that the optimal length for the interior edge ranges roughly between 0.01 and 0.02. Oops, sorry for this. So, right, but the limitations of these approaches are that they are all based on simulations, and what we wanted was to mathematically analyze how the branch lengths, for instance, of the interior branch, influence the tree reconstruction. And first of all, we will do this now for maximum parsimony, but we will look at the other methods later on. Well, there's some facts are already known. For instance, in 2002, Mike Steele and Laszlo Csekely investigated a tree, the 4-taxon case, where you have the short interior branch of length x and the 4 pending edges of length y. And they found that then the reconstruction, or the number k of characters needed to reconstruct the true tree, grows at a rate of x to the -2. However, what happens if you, say, fix the ratio x over y, and then search for a length of the interior edge that actually minimizes the number of characters needed. So this is what Yang kind of did in his simulations, but we wanted to do this mathematically. So our setting, as I said, we are looking at the 4-taxon scenario. We choose the interior edge to have length x and the pending edges to have length p times x, where p is a number larger than 1. And we consider the two-state symmetric model, which is a simplification of, say, the DNA uses obviously 4 character states, so we are only using 2, say alpha and beta. And the model is called symmetric because we assume the probabilities, the substitution probabilities from alpha to beta or from beta to alpha to be equal. So what we found out then is, this is a long theorem, but I'm going to simplify it in a minute, is that if you generate k independent and identically distributed sites under this two-state symmetric model, then the maximum parsimony for the maximum parsimony reconstruction probability to be at least 1 minus epsilon, you require k to be larger than a constant times p squared for any x. And if k is such that it's larger than a constant times p squared, then there also exists such an x that provides you a reconstruction probability of 1 minus epsilon. Now, what does this mean? Well, we call a reconstruction reliable if its probability is at least 1 minus epsilon for the and basically you can choose the epsilon. And then this means that the number k of characters needed to reconstruct your true tree grows at a rate of p squared, at least at a rate of p squared, and there is an x, namely at least for the optimal x, k will grow at a rate of p squared. So, so you do not have to be afraid of a growth of p to the power of 3 or so, because there is always an x for which k grows at a rate of p squared. So I will show you a sketch of the proof now. Well, in the 4-taxon case, there are obviously 3 possible trees. You can either have taxa 1 and 2 grouped together versus 3 and 4, or you have 1 and 3 grouped together, or 1 and 4 grouped together. And let's assume for now that T1 is the true tree. Then we introduce the random variables xi, which we set equal to 1 if the ith character in our sequence or corresponds to the interior edge of tree T1. So if the ith character is, say, alpha, alpha, beta, beta, it's the same partition that is induced by the first tree. Similarly, we set it to -1 if it corresponds to the interior edge of tree T2, and to 0 otherwise. So if it supports the third tree, or if it's an uninformative character, we will set xi to 0. We assume that these xi's are independent and identically distributed, and then we introduce the random variable zk as the sum of the first k such random variables xi. And then, since this is a sum of independent and identically distributed random variables, we can apply the central limit theorem, which says that then the random variable zk is approximately normally distributed. And what is the intuition behind all this? Well, look at this random variable zk. Basically, we are summing up 1s, -1s, and 0s. I mean, obviously, we can forget about the 0s. Now, this whole sum will be positive if and only if we have more 1s than -1s. And that means that we have more characters supporting the first tree than the second tree, which means that the true tree T1 will be favored over T2 if and only if this random variable is positive. Okay? And the nice thing about the xi's being independent and identically distributed is that then for the expected value and the standard deviation of zk, we can find nice and easy formulas that only depend on the number k and the probabilities of x1 being equal to 1 or -1. Now, this is obvious because okay, since they are identically distributed, you do not need to worry about the probability of x2 being something. It's the same as x1 being something. And the probability for the 0 cancels out because in the expected value, it obviously appears 0 times. So this gives us a nice formula. And the nice thing then is that for these probabilities in the two-state symmetric model, there's a well-known way of expressing these probabilities with a so-called Hadamard representation. So you get these formulas, and this theta here is e to the minus 2x. Remember that x was the length of the interior branch of our tree, and this p here was, remember that p times x was the length of our pending branches. Okay? So the whole formulas depend only on p and x, and the expected value and the standard deviation only depended on k and these two formulas. So altogether they depend only on k and x and p, and thus if we fix p and look at this ratio, we can find an x that minimizes k. So this is roughly the idea of our proof. Anyways, let me summarize what we just found. So for maximum parsimony, the number of characters needed to reliably reconstruct the true tree grows at a rate of p squared. Now naturally, you might ask me, can we do better with another method? And it turns out that no, we can't. And we have shown this using an argument with the so-called Hellinger distance. So you cannot do better than a rate of p squared. You will never have linear growth. Okay? So what can be done in future? Well, first of all, you might, instead of looking at a tree with 4 equal pending edges, you might allow 2 of them, one on either side, to grow. So this would mean you approach the Felsenstein zone. Of course, then the number of characters needed to reconstruct the tree will go to infinity. But it might be interesting to see how fast this actually happens. Another thing is that, as Churchill, von Heseler, and Navidi found, making the pending edges shorter might give you better results. And they suggested that you do not only there are several ways of doing this. You can, for instance, just add more taxa to your tree, and thus shorten the relative length of your pending edges you are interested in. So adding more taxa can improve your results, and that is something you could also mathematically analyze. So this also could be done. Yeah, then I want to thank a lot of people. First of all, you for listening, and yeah, that's it then for now. And before I answer any questions, since I was talking now all the time about the true tree, I want to show you one true tree.
Okay, any questions? So,
Oh, yeah?
When you say that cannot be improved by other methods,
Yes?
what are the other methods you consider?
Yeah, for instance, maximum likelihood or neighbor joining. It doesn't really matter because our argument shows that you cannot do better. So no matter which method you use, you will not improve the result.
It's a theoretical result.
Yeah, so it's a theoretical result that will be a basis for all methods. So you cannot do better. You do not have to try all the methods to get this result.
Yes, please.
Is there any intuition as to what would happen with different number of character states?
If you consider the 4 taxon case, my intuition is that the result might not change, because if you look at a character with 3 or more states and you only have 4 taxa, then this will be an uninformative character. So in our definition, it will appear with value 0 anyway. So my intuition is that it might not change the overall result. But I have not really did all the math, but I think that's what I basically say. Okay.
So that you can't do better was that you showed for this 4 taxon tree with all pendant edges.
Yes, yeah, that's right. Yeah, all the results only apply to that tree for now. Yes, that's right. Okay. Yes?
Like a take a specific kind of tree, like the caterpillar tree we heard about before, or just a completely sort of bifurcating tree, and you look at all the quarters that are in there, and then They are not necessarily of one of those types, but somehow they may approximate one or the other. So you have the P and the X for all these quartets. Do you have any kind of statistics on what to expect for X and P for these various types of quartet trees? You get subtrees of standard trees.
No, I haven't really looked at that, but I think that is why first when I looked at it for the first time, I thought, well, 4-taxon tree is not really a good example for a tree, but of course you're right, it's very important because of the quartet reconstruction. So yeah, this would be a next step to look what it does if it's actually employed in a larger tree. Yeah, that would be good. But yeah, we do have a formula though for the optimal value of X in our setting, but we have not looked at what happens if you add more taxa to the tree. Okay.
If there are no further questions, then please join me in thanking the speaker again.